Let's talk about the idea of angular speed. This relates to the topic of arc length, and we're going to use the formula developed in the previous video that describes theta in terms of arc length compared to radian measure. So linear velocity and angular velocity are related in the following setting. Suppose there's a point or some sort of object that's spinning. So a point moving in a circle can be described in a couple ways. We can consider the rate at which that circle is moving through space. That relates to the linear velocity. But we can also think about the angle that the object is spinning through and the rate at which that angle is changing, and that relates to angular velocity. And those are related by the formula we talked about earlier, theta equals arc length divided by r. So let's take a look at how that relationship works. So s and r are both linear measurements, and in this setting r is fixed. So the two measurements that are actually changing are going to be s and theta. If we have a fixed rotation, a point moving around a circle with a fixed radius, r is going to be the same, r is going to stay the same, but s and theta are going to change, but they're going to change in coordination with each other as we move, as the arc length changes, as we move around the circle and the position on the arc changes, the angle also changes. So we can use the following form. If I multiply both sides by r, we get the relationship s equals r times theta. And what I want to compare is the rate of change of theta and the rate of change of s, the rate of change of the arc length. The rate of change of the arc length, that corresponds to the idea of a linear velocity, because it's talking about the change in a linear measurement. And we're going to describe that with the symbol v for velocity. On the other hand, theta, the angle measure, relates to, the change in theta relates to angular velocity. And angular velocity is described with the Greek letter omega, which looks a little like a curly W. An important thing to keep in mind is how we measure these things. Angular velocity, the value of omega, is measured in radians per unit time. And so we could think of that, typically that will be in maybe radians per minute or radians per hour, or we could think of it in terms of revolutions per minute or revolutions per hour. Velocity is described by some sort of linear measurement per unit time. So we could talk about miles per hour or feet per second. So the key formula that we're going to use is the v equals r times omega formula that relates angular velocity to linear velocity when the radius remains constant. Suppose there's a flywheel, a piece of spinning equipment. Suppose there's a flywheel with a diameter of 9 centimeters and it's rotating at a rate of 15 radians per second. We want to figure out the linear speed of a point on the rim of the flywheel. So to sketch out the problem here, we have this flywheel, we have a point on the rim, and we know it's rotating at a certain speed. We also know that the diameter is 9 centimeters. So thinking about our formula, v equals r times omega, let's think about what we know. I have two values from the problem. I have 9 centimeters, I have 15 radians per second. Well, radians per second. Radians suggests that we're talking about angles. Radians per second is our value for omega. So omega equals 15 radians per second. The value 9 is given as the diameter, so it's not quite the R value that we'd like, but it's related to it. The radius is exactly half of the diameter, so if we take that diameter value divided by 2, 9 divided by 2 is 4.5. And so the radius would be 4.5 centimeters. Well, with those two values in hand, we can apply them to the formula here, and so we get that velocity is 4.5 centimeters times 15 radians per second. So with a calculator, we could multiply that out and get an answer. 4.5 times 15 turns out to be 67.5. Let's think for a moment what our answer should be. It turns out, as we mentioned before, the measure of radians, it's actually a unitless measurement. So in these sorts of calculations, the radian part will kind of fall away, and so we end up with centimeters and seconds. And so this is a velocity, and it's a velocity in terms of centimeters per second. But we'd like the linear speed in terms of centimeters per minute. We want to take 67.5, which is in centimeters per second, and translate that into a value in terms of centimeters per minute. To do that, I want to cancel out the seconds in this expression, in the units. And so I'm going to multiply by a conversion factor that has seconds on top and that replaces that with the value, the units that we'd like. So I'm going to put seconds on top and I'm going to put minutes in the denominator. Well, how can I compare seconds and minutes? There are 60 seconds in 1 minute. So 60 over 1, 60 seconds over 1 minute is essentially equal to 1, in the same way that 180 degrees over pi is equal to 1. And so multiplying that out, if I take 67.5 times 60, I get 4,050. And that 4,050, because the seconds canceled, is going to be in centimeters per minute. So that's the final answer that we're looking for. The point on the rim of a flywheel that has a diameter of 9 centimeters and is rotating at a rate of 15 radians per second, that point will be moving through space at a velocity of 4,050 centimeters per minute. Let's take a look at a second example, and what I'd like to do is take a look at the problem, set it up a bit, but then pause and give you the chance to try to think through the rest of it. So this problem involves a carousel, something you might find in a park with horses that spins around, and there's a seat on the carousel that is 18 feet and 9 inches from the center. The seat is traveling at a speed of 15 miles per hour, and we'd like to figure out how many revolutions per minute the carousel makes. So we're going to use the formula that we used in the earlier example. Linear velocity equals the radius times omega. And so what I want to think about for a moment is how does the given information relate to that formula, 18.9 inches and 15 miles per hour? Okay, well, let's think. So 18.9 inches, that's the distance from the center. that corresponds to the radius. 15 miles per hour. Miles is a linear measurement, and so this is linear velocity. That corresponds to v. So for this problem, what we know, we have a value for v and we have a value for r, but we don't know omega. So omega is the thing that we're trying to figure out. What makes this problem a bit of a challenge is that there are a bunch of different units involved. There's feet, there's inches, there's miles, and we'd like to figure out the value for omega, but it's not going to be in radians per minute. We want to then translate that into revolutions per minute. So try to set things up, try to get things started with the formula. There's a lot of conversion to think through. In a separate video, I'll discuss the answer, but do please take a few minutes and try to work through the problem. I hope you enjoyed the video. Thanks for watching.